Okay, here it is 14.1 on graphs, paths, and circuits. What you're learning in this section is you'll understand the relationships in a graph, model relationships using graphs, and understand and use the vocabulary of graph theory. Okay, so graph theory can be used to solve the following types of problems, and that's what we'll be doing and covering in this chapter. So we can do a more user-friendly map for a city subway system, for example. Public works administrators must find a more efficient route for snowplows, garbage trucks, and street sweepers. A sales director traveling to a bunch of different branches of his office need to minimize the cost of the trip. You need to run a series of errands and return home using the shortest route. After a heavy snow, maybe campus services must clear a minimum number of sidewalks and still ensure that students walking from building to building will be able to do so along cleared paths. Or you may need to represent the parent-child relationships for 5 generations of your family. So these are all the different types of things that you can do using graph theory. Now, the most famous use of graph theory is the 6 degrees of separation, basically stating that anyone in the world can be joined to any other person through a chain of no more than 4 intermediate connections. So, for example, here we only have 2 intermediate connections connecting Oprah Winfrey with Steve Jobs. And so, here Oprah Winfrey is connected to George Bush because Oprah had a candidate Bush on her show in 2000. And then between George Bush and Bono, as president, Bush held a working meeting on Africa with Bono, and then between Bono and Steve Jobs, because Bono bought his New York City apartment from Steve Jobs. And so here we have, just the 2 degrees here in between. And so we could have four, and that would give us the total of 6 degrees if we had two more possibilities in between. So that's kind of how graph theory works. We're going from one person to the next to the next. So, definition. A graph consists of a finite set of points called vertices, and if you want to do only one, it'd be a singular, it would be a vertex, which would be labeled as black dots, and line segments are curves called edges that start and end at vertices. An edge that starts and ends at the same vertex is called a loop. So, what we have here, all these black dots, those are going to be the vertices. Now, each line here, whether it's going whichever direction, those are going to be called an edge. And then when we start and end at the same place like this, we call that a loop. Okay. Now, just because these cross here, that doesn't mean that's a vertex. The vertex only has a black dot. So this one just means this one's passing maybe over the top, and this one is passing underneath. And so they're not actually touching, they're kind of going around each other. All right, so like it says here, the four vertices are labeled A, B, C, D. And the vertices A and D are connected to form a line segment which is parallel to another line segment BC. And then the vertex C is forming a circular loop, like I talked about here a little bit ago. And the line segments are AD, and we have DB, and we have AC, and we have BC. Now, the point of intersection of BD and AC, again, is not a vertex. So remember that's not a vertex. All right. So two graphs are equivalent if they have the same number of vertices first, and they're connected to each other in the same way. So the placement of the vertices and the shapes of the edges are unimportant because we can see these two graphs are equivalent because we have one, two, three, four different vertices. Here we have one, two, three, four different vertices that are labeled the same, and they're connected in the same way here. A is connected to B, A is connected to B, B is connected to C, B is connected to C, and then C is connected to D, and C is connected to D. Now, they don't look anywhere the same, but because they are the same number of vertices and are connected in the same way, they are actually equivalent graphs. So now let's do one for us and see, are these two graphs equivalent? All right, so let's draw on here. And so what we have here is, let's get that out of the way. We have one, two, three, four, five different vertices. Here we have one, two, three, four, five different vertices. So that's good. And now we have to kind of think about how they're connected. So we have A is connected to B, so that's one. Here A is connected to B, that's one. And then B is connected to D, so let's call that two. B connected to D, so that's two. And now D is connected to E, so let's call that three. D is connected to E, let's call that three. And then we can have E is connected to C, so that's four. E is connected to C, so that's 4. And we have C connected to A, so that's 5. C is connected to A, that's 5. We also have B connected to E, so let's call that 6. And that was B is connected to E, so let's call that 6. And then we also have the C and D connected, so let's call that 7. And so that C to D, that's 7. So we have 5 vertices. They're all connected in the same way. So yes, basically they are equivalent. And again, they have the same number of vertices and they're connected in the same way. Okay, so because of that, they are equivalent. All right, so let's stop that. And so let's pause here and we'll come back in a second.